Welcome to my next presentation all about using matrices to calculate curl equations. That's where we're going to go to. In the meantime, I just need to define a few terms. So first of all, what is the matrix? Now there will come a very short clip on the matrix, which is a film.
The answer is out there, Neo. It's the question that drives us.
What is the matrix?
Now the dictionary says a matrix is from the mater, or from the mother. It is the womb, the cavity in which a fetus of an animal is formed and nourished to its birth. A mould, the cavity in which anything is formed and which gives it shape, as a matrix of a type. The place where anything is formed or produced, as a matrix of metals gang. In dyeing, the 5 simple colours black, white, blue, red and yellow, of which all the rest are composed. Now of course in mathematics and physics it's a completely different definition of a matrix, but that's kind of where linguistically we start. First of all, we need to revise coordinate systems. How are they different? Where we normally work in terms of rectangular coordinates, we have x axis, y axis and z axis, and these are mutually orthogonal, which means they're right angles, and this gives us a three-dimensional approach. You have x axis, y axis and z axis coming to the top of the page, and you have a point defined as point x, y and z. Then you can have cylindrical polar coordinates, which forms a cylinder, which you have x coming out, y going that way and z going up, and then you have a distance r from a point here, and the distance here, instead of being x, y and z, is now defined as r, phi and z, and phi is the angle from the x-axis to the position r vector here. So you've got a point now in 3 dimensionals defined as being a distance r at an angle phi and on the z-axis, point z. And probably the hardest one is the spherical polar coordinates, which are you have x, y and z equivalent here. You have r, theta and phi. So theta goes between 0 and pi, and phi because 0 and 2 pi goes right round. So we're going to look ultimately at the spherical polar coordinates, but let's start off with rectangular coordinates, how we do a matrix calculation. So in a curl of an A field using matrices, so first of all you have here the curl cross del cross A, and then you have your unit vectors Ex, Ey and Ez. And then the next line is the partial differential of d by dx, d by dy and d by dz, and that part of the A field which is in the x component, the y component and the z component. And what is really helpful to remember is I put these signs here, these signs positive and minus positive. They show you how the calculations change when you go from the first column, which is positive, the second column which is negative, and the third column which is positive. So when I choose the first column, I choose Ex, the unit vector here, so plus, because it's the first column plus, Ex, and then I ignore everything on the same row and everything on the same column as I've done here, and then I go top left, bottom right, minus top right, bottom left. So it's top left d by dy of Az, d by dy of Az, minus d by dz of Ay, minus d by dz of Ay. The next one, if you remember that the middle sign is going to be negative, I always take the minus sign outside, put it here, and then just do exactly the same procedure, minus Ey, and then I go top left, d by dx of Az, d by dx of Az, minus d by dz of Ax, minus d by dz of Ax. And then finally you take the third one, again ignoring all along the row and the column, Ez, and it's a plus because a plus sign above here is a plus, and it's top left, bottom right, d by dx of Ay minus d by dy of Ax. There we go. Then write it all out in full, and you have del cross A equals unit vector Ex, and you'll see that you then have no component of x in that particular expression. So you have d by dy of az minus d by dz of ay minus ey, and then you have no y component in here either. Then it's d by dx of az minus d by dz of ax plus, third column, d by dx of ay minus d by dy of ax. That's the easy one. Now, let's have a look at the curl of an A field, and this is a B field, which is magnetism, the curl of an A field in polar coordinates. And then you have the determinant outside, which is 1 over r squared sine theta. And when you get into the same procedure, you have column, first column is plus, second column is minus, third column is plus, and you have the unit vector now r hat, r theta hat, r sine theta, phi hat, d by dr, d by d theta, d by d phi, ar, r a theta, r sine theta, a phi. So you have r down here, theta here, and phi here. It looks initially difficult, but use the same procedure. So we take the first column, r hat, it's a plus, so you have the plus at r hat, and you go top left, bottom right, d by d theta of r sine theta a phi, d by d theta of r sine theta a phi, minus d by d phi of r a theta, minus d by d phi r a theta. Second column, you take the second column, you've got a minus, so put the minus sign outside first of all, and you're using r theta hat, and then you do the same procedure, d by dr of r sine theta a phi, minus d by d phi of ar. And then finally, the third column, which is a plus, the unit vector r sine theta phi, ignore the row, ignore the column, top left, d by dr of r a theta, minus d by d theta of ar. And then when you put it all together, and this is where it becomes quite difficult to do in a mathematical equation software, and it's just being a little bit of a purist here, as I tend to not try and put it all onto one line, but for example, I know I've got an r squared sine theta here, 1 over, multiplied by all that which is in the bracket, and it makes it easier then to have that bracket represented by here. So nice curly brackets, and the dot 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 refers to this expression here, and it's again, like we said before, if the unit vector is r, then there's nothing that determines upon r. There and there, there and there. R theta, there's nothing that depends on the theta here, nothing there or there, there or there, and phi, nothing that depends upon a phi here. So r d by d theta r sine theta a phi minus d by d phi r a theta minus r theta d by dr of r sine theta a phi minus d by d theta d phi of ar plus r sine theta d by dr r sine r a theta minus d by d theta ar. It's a wonderful symmetry here because you go r theta hat, r sine theta phi hat, d by dr, d by d theta, d by d phi, ar, r a theta, r sine theta, a phi. There we go. Here endeth the lesson, and there are some references there for you to have a look at. So the YouTube clip of matrix, quite different of course in real life using mathematics, the Webster's Dictionary of the term matrix, hyperphysics, which is really good for looking at all the coordinate systems and other good stuff of physics stuff, and the Open University where I used to work with the Residential School of Electromagnetism. I hope it's been useful. Thank you for listening. Bye.